p orbital. So remember, the s orbital has only one orbital, or the s subenergy level has one orbital, and p subenergy level has 3 orbitals. And then when L is equal to 2, then we have what? Magnetic quantum number is equal to 5. So for this case, we have 3d orbital. So 3d subenergy level. So it means that how many? So listen. So here we have one s orbital, 3 p orbital, or p subenergy level, or 3 orbitals of p. So 1 orbital of s subenergy level, 3 orbital of p subenergy level, 5 orbitals of d subenergy level. So total number, so if you say the total number of what? Of orbitals, okay, in what? N is equal to 3 is what? 1 plus 3 plus is 9 plus 5. So 5 plus 3 plus 1 is equal to 9. So in n, principal quantum number n is equal to 3, we have 9 orbitals. 1 orbit of s subenergy level, 3 orbitals of p subenergy level, 5 orbitals of d subenergy level. Hey, be careful, my dears, too. I understand that how things might confuse you. I understand, because even myself, I remember how I suffered a lot on learning them and keep them in my mind, because learning is not a process, it's not a challenge. The challenge is to remember, it means that to transfer the materials in your exercise book or in the textbook into your brain. That's a challenge. So now let me just let us do for n is equal to 4, then I'll leave n is equal to 5 as your homework. So when the principal quantum number is equal to 4, here we have 4 subsidiary quantum number. The first one, n is equal to 0. So here, magnetic quantum number is equal to 1. So we have only one s orbital. But because the principal quantum number is equal to 4, this in chemistry, we don't write 1s, we write 4s. Right? I will teach you in next lectures and what about this in electronic configuration. Again, the second subsidiary quantum number is L is equal to 1. So when L is equal to 1, the magnetic quantum number is equal to 3. So you have 3 orbitals of p subenergy level. So because the principal quantum number is equal to 4, and I told you in lecture 12 about this coefficient, so this we write in electronic configurations as 4p. Again, we have the next subsidiary quantum number, which is equal to 2. So in this, magnetic quantum number is equal to 4, or is equal to 5, sorry. Because 2 times 2, it is 4, 4 plus 1 is equal to 5. So M is equal to 5. So here we have again 4d. So you have 5 orbitals of d subenergy level. Again, we have the next subsidiary quantum number, which is L is equal to 3. So when L is equal to 3, magnetic quantum number is equal to what? Is equal to 7. So this is 4f orbital. So you have 7 orbitals of f subenergy level, right? So total, how many orbitals do you have when the principal quantum number n is equal to 4? So you have 1 plus 3 is equal to 4, plus 5 is equal to 9, plus 7 is equal to what? 16. So we say that the total number of orbitals, in principal quantum number is equal to 4 is what is, because we say that we have 9 is 16. So interesting. So it's 16. So now your homework. This is homework 13. I can give you homework at the end of the session, at the beginnings, in the middle of the session. So how many orbitals does this principal quantum number contain? So command A, when n is equal to 6, command B, when n is equal to 5. So work on those principal quantum numbers. So now we can identify the total number of orbitals, and also remember the total number of orbitals will be, or the twice of the total number of the orbitals will be equal to the number of electrons accommodated in that energy level on that principal quantum number. Okay. So if that's the case now, I would like just to take you to another part about the magnetic quantum number. We say that values of magnetic quantum number. We say that the magnetic quantum number is restricted by subsidiary quantum number. So this is restricted by subsidiary quantum number. It means it depends on the subsidiary quantum, restricted by subsidiary quantum number L. Quantum number L. It is always represented by the following values. The first one is represented by what? By 0. By 0 may be represented by 0, and also may be represented by positive integer, and also we may represent the magnetic quantum number by negative integer. So let me explain what does it mean. So we may represent the magnetic quantum number by using 0. We may represent magnetic quantum number using the positive integers, or we may represent the magnetic quantum number by using the negative value. Okay. So that is from negative L to L including 0. Thus it is from negative L to positive L. So you have to be careful when you be learning about magnetic quantum number, because there are two things that you should not confuse. Means now I want to take you deeper. And the question is, for example, when L is equal to 0, we have 1. When L is equal to 1, we have 3. What does it mean? When L is equal to 2, we have M is equal to 5. What does it mean? What the meaning? So now I want to take you deeper. Say deeper. Okay, so I want to explain in detail what this means. M is equal to 1, M is equal to 5, M is equal to 7. What does it mean? So we say that to clarify means that to represent each orbital, or the general formula, we say that the general formula that is used to present each orbital found in the sub-energy level by using magnetic quantum number is given as, we represent it from negative L, and then from L we move to 0, and then we go to positive L. So very important general formula. Let me clarify in a simplest language for you to understand from the simple example, because my intentions, I want you to love chemistry, so I want to simplify things, and I say that I would like to take you deeper. So let us start with this, the fundamental or the ground level, which is n is equal to 1. This we call theoretic principal quantum number. Listen carefully. And then from this principal quantum number, we may get to a subsidiary quantum number. So the subsidiary quantum number will be n minus 1. So for this case, is equal to 0, right? In terms of sub-energy levels, this we call the S sub-energy level. Again, today I taught you about magnetic quantum number. So it's a magnetic quantum number. To find the total number of orbitals in this S sub-energy level, we have to take 0, and then we have to use this formula. We say that is twice L plus 1. So take 0, substitute in L, I get 0 times 2 is 0 plus 1, so we get to it 1. And then we say that here we have only one S orbital. Forget about maybe having coefficient there. So what does it mean? So this means that under this case, when m is equal to 1, in representations of the sub-energy level, we say that when L is equal to 0, also in terms of representation, m is equal to 0. So we have represented the magnetic quantum number by using L as a restrictions by using 0. So that's why we say that this is one sub-energy level, because the value of magnetic quantum number is only one value, which is 0. Listen carefully. And then, if we go, n is equal to 2. That is a principal quantum number, n is equal to 2. So then, here we have two subsidiary quantum number. The first one, L is equal to what? To 0. So when L is equal to 0, by using this formula, we know that even m also is going to be 1. Right? And then by using the same formula, we concluded that, okay, here we have one S orbital. Listen carefully, listen carefully, listen carefully. So in terms of representations of orbital now, by using magnetic quantum number, this will represent as m is equal to 0. Because there's only one S orbital. Again, the second value, which I was looking for, very interested in, is L is equal to 1. So L is equal to 1, when we take 2 minus 1, we get L is equal to 1. Right? So in this one, by using this formula, if you substitute L is equal to 1, we get 2 times 1 is 2 plus 1 is 3. Right? And then we say that here we have what is 3 orbitals. And these 3 orbitals are in what? P sub-energy level. Listen carefully. So how do you represent these 3 orbitals? That the questions comes right now. These 3 orbitals, we can represent them as a magnetic quantum number, but by restrictions with what? This what? Value of L. How do you represent them? We say that these 3 orbitals, the year representation, will be from negative L, comma 0, comma positive L. This is what I told you. So what do you mean? When L is equal to 1, then the 3 orbitals will be represented by these values of magnetic quantum number. So it will be negative 1, comma 0, comma positive 1. So this is the first orbital. This is the second orbital. This is the third orbital. That's why we say that when M is equal to 3, we have 3 orbitals. Interesting. Okay, so that's why. So it means that you have 1, 2, 3 orbitals. And this is the way that we present by using subsidiary quantum numbers. Because L is equal to 1. Okay, maybe you didn't understand clearly. Stay tuned, stay there. I will make sure that you understand. Even if you don't want to understand, you will understand. Don't worry about that. I was surprised. I was even frightened when I knew this secret. I spent much time. I asked many people to explain to me, or different teachers or different my colleagues to explain to me, but they didn't manage to explain to me. As I said, just ask me to create, which actually is a difficulty activity on my side. So when n is equal to 3, listen carefully now. I believe when I will be ending on this example, because it's the first example, second, third example, you will understand how we represent it, or how we represent the principal quantum, the magnetic quantum number. And then now here, for this one, let us label them because M is equal, so this is M1, and also here we say that this is M1, and even this one, this we say that this is M1 is equal to, and here we have M1 is equal to this. So we have N is equal to 3. The first sub-energy level is what? When we have 3 minus 3, so it's equal to what? To 0. According to this formula, listen carefully, listen carefully. So according to this formula, when you substitute 0, we get that 1. That is fine. So that is S orbital, but it's 3s orbital. So I told you that this we label as 3s orbital, sub-energy level. Good. Then in terms of magnetic quantum number now, we say that M1 is equal to what? So because you have only one orbital, because L is equal to 0, the limitation, so the value of magnetic quantum number will be 0. Because the value of subsidiary number is only 0. Then we go when L is equal to 1. So when L is equal to 1, if you be looking the magnetic quantum number without subscript of 1, in total, the total number of orbitals, take 1, multiply by 2, get 3, plus 1, we get 3. Right? So here also we say that we have 3 p orbital. But now, in case of, we want to know the representation of these 3 orbitals. So I told you that, for that case, magnetic quantum number is equal to negative L, comma 0, and then to what? Positive L. Right? We said you have 3 orbitals, you have to show how do you present them, so use the magnetic quantum number. So by using the magnetic quantum number, M1 is equal to what? What the value of L here? It is 1. Be careful. Okay. So this is negative 1, comma 0, comma positive 1. So that's why we say that there are 3 orbitals in p sub-energy level. We continue. The third value, L is equal to 2. And L is equal to 2, it means we take 3 minus what? 1. So when L is equal to 2, we say that the total number of orbitals, M, we take 2 times 2, it is 4, plus 1, it is what? 5. So you have how many orbitals? 5 orbitals. How do we represent them? The way we represent them, we say that M1, according to the general formula, is negative L to 0, and then to positive L. This is a lowercase L. So if that's the case, you say that this is M1, listen. So it means that this goes to 0, simply that negative 0. We can say that dot, dot, dot to 0, and then dot, dot, dot to positive L. So I think that it's better if I give you this kind of denotation. It will help you for the general formula. Negative L, 3 dots, then we have 0, 3 dots, then positive L. So now we have the value of L is equal to 2, so listen carefully. So the first value of negative L will be negative 2, then the next value after negative 2 will be negative 1, the next value will be 0, next value on the number lines will be positive 1, next value on the number line will be positive 2. Interesting. So now we have how many orbitals? 1, 2, 3, 4, 5. How many total orbitals that we found when L is equal to 2 is 5. The representation magnetic quantum number is what? Negative 2, negative 1, 0, positive 1, positive 2. Okay. So that's the case. So it means that this is what we call the d orbital. So this is the first orbital. This is the second orbital. Those are the values. This is the third orbital. This is the fourth orbital. This is the fifth orbital. Okay. So then, number 4, when n is equal to, let me add the last question, n is equal to 4, our main focus, because we have L is equal to 0, L is equal to 1, L is equal to 2, L is equal to 3. So I would like to leave L is equal to 0 to, from 0 to 2 as your homework, because I've told you. I would like to deal when L is equal to positive 3. Right? So when L is equal to positive 3, its total number of orbitals will be 3 times 2 is equal to 60 plus 1. I told you, and we have already discussed it, and you've understood that it's equal to 7. So it is how many total number of orbitals? 7. Because there's a close relationship between the number of orbitals and the way we use this magnetic quantum number to notate. Because remember that we said that it's used to differentiate orbitals or subenergy levels of the same orbitals that have the same shape and the same and same energy, but have different directions when they are subject to the magnetic field. So for this case now, we say that, remember the general formula of magnetic quantum number. So I told you that is what? From negative L, then continuing to 0, then continuing to positive L. Listen carefully. So it means that our first magnetic quantum number for this case now is equal to what? Negative 3. So that's the first orbital. The next is equal to what? Negative 2. At the second orbital. And again is equal to what? Negative 1. At the third orbital is equal to what? 0. At the fourth orbital is equal to what? Positive 1. At the fifth orbital is equal to what? Positive 2. At the sixth orbital is equal to what? Positive 3. At the seventh orbital. So these are the 7 orbitals. So look, let us count together. 1, 2, 3, 4, 5, 6, 7. 7 orbitals. And what the name of this orbital? We say that this is F40, F sub energy level. It has how many orbitals? 7 orbitals. So it means that in this orbital we can place maximum 2 electrons, maximum 2 electrons, we can place maximum 2 electrons, maximum 2 electrons, 2 electrons, 2 electrons, 2 electrons. So it means that the F sub energy level can occupy or accommodate how many electrons in maximum? 14. How many electrons does the d orbital contain? The maximum number of electrons. Because it has 5 orbitals, can accommodate only 10 electrons. Interesting. How many electrons can the p orbital accommodate? The p orbital. How many electrons can it accommodate? 1, 2, 3, 4. Then 1, 2, 3. So it's 6 electrons. For the s orbital, only it can accommodate only 2 electrons. In case you have questions concerning about what I've been teaching you, don't hesitate yourself to ask in the comment section, because I know that this concept is confusing many A-level students and can confuse you for a long time, because to get the comprehension of how stuff goes is a little bit challenge. Then, So if that's the case, we can even think that, yeah, so in the terms of the total of number of orbitals, okay, that's enough. So since an orbital can take a maximum of, that is enough. And the two electrons having the same value of n and 1 and L with different values are degenerate or have the same energy. So let's say we have a question sometimes. What is the meaning? What is the meaning of degenerate? What does it mean with the term degenerate? Say degenerate. Degenerate. So that's the terminology that I have defined. Degenerate. So degenerate. What the means of the word degenerate? So we say that degenerate, by definition, we define it as the n are two electrons having the same value of So we say that degenerate is a state whereby two electrons have the same principal quantum number n and the same, so I think that, let me write in words, the same principal quantum number, the same principal quantum number n, and the same subsidiary quantum number. And the same subsidiary quantum number, which is L, but different, we have different magnetic quantum number, different magnetic quantum number, which we call the M1. So for example, we can have the degenerate. We say that, let's say n is equal to 4, and then say L is equal to 3, and then the magnetic quantum number is -3 and -2, right? So the two electrons, for example, electrons that is found in this orbital and this orbital, they have the same principal quantum number, which n is equal to 4, right? They have the same magnetic quantum number, which is L is equal to 3. So that's what we call it degenerate. Very important terminologies. If you refer some of the past papers, you might find. Okay, so in case you have any question concerning about the magnetic quantum number, don't hesitate yourself asking in the comment section. I understand that if you understand this stuff, your life in organic chemistry, will be easy, because will be it means that the organic chemistry, for example, it will be using a lot about the electronic configurations, which is advanced electronic configuration, not like the one that we wrote during the O-level studies. So make sure that you tell me or you ask your questions in the comment sections. But that's the beauty of digital system. When I recorded this lecture, you can review it and revise it several times as you can, even 3 times. Watch this video 4 times, 5 times, 6 times, 10 times, because it will help. It means that you'll understand at each concept at the time when you'll be reviewing this video. So that's the one thing that I want to insist you, and that's all about the magnetic quantum number. Right now, allow me to teach you about spin quantum number, which is the last quantum number at this level. Okay? So then now we go for number 4, the first quantum number. We call it spin, say with me, spin quantum number. It's not long. It's not long like the second and the third. Spin quantum number, very short. Spin quantum number. And this spin quantum number, we use the notations of MS. The fundamental questions which I insist you always to ask yourself, what is the meaning? What is the meaning of spin quantum number? So that's the fundamental question you have to ask yourself. Okay, there are many definitions, but I found one which is very important. We say spin quantum number is a quantum number. The quantum number. So this is the quantum number. So this is the quantum number which gives the direction in which, so this dealings with directions of electrons, in which electrons are spinning, in which electrons are spinning. So which electrons are spinning. So spin quantum number is the one of the quantum number which gives the direction, gives what the directions in which electrons are spinning. So spinning means that the orientation of electrons. So this principal quantum number, or this quantum number, does not tell us about the shape or the number of orbitals. No, remember the principal quantum number? It's an energy level that found in the shell. Subsidiary quantum number gives us shapes, and even the number of sub-energy levels, and even the names of sub-energy levels. Magnetic quantum number gives us the number of 40 orbitals in each sub-energy level. But this one is tell us, or it gives us information about the direction in which electrons are spinning. So again we say that the spin quantum number, takes either of these two values, either positive half or negative half. It takes only those two values. It's fine, quantum number can take either positive half or negative half. So you may use m subscript of s or lowercase s. So it is noted as what? M subscript of s or s. So spin quantum number is noted m subscript ms or s. So what does it mean? We say that one, when the value, or when the spin quantum number takes what? positive half. Means that electrons indicate, means that the electrons is spinning in clockwise direction. It takes positive half, then means that